in this conference. I would like to first find out if we can, if you can see my shared screen.
Yes, you can see.
Okay, thank you. My field of specialization is in numerical analysis, and in particular a marriage between numerical analysis and dynamical systems together with other areas. So what I would like to talk about this morning relates to an area of research which has become increasingly indispensable as a result of what we are experiencing, the proliferation of numerical methods and their use in the solution of engineering and scientific problems. So the area that I would like to speak on relates to numerical flow K-theory. We all know flow K-theory from a continuous perspective, but when we use a numerical method to solve a periodic system, we often end up with a discrete system whose dynamical properties may not be known. I would like to apologize that my camera doesn't seem to be working at the moment. The outline of my talk give a little bit of motivation and state a few things about continuous flow K theory. I'll explain exponential dichotomy. We'll talk about the discrete framework, a rigorous preservation result, and then we are going to introduce a linearized collocation scheme, do a nonlinear extension, and then do some modern extensions which have to do with what is happening now. And then I'm going to end with some outlook and a research program that those who are interested might be able to engage in. Let's take a simple one-dimensional periodic non-autonomous system that is given there. It's non-autonomous because the right-hand side depends on t. It is periodic because the function on the right-hand side, f, is t-periodic. When we analyze a system of this sort, we are going to replace equilibrium solutions with a periodic orbit because the solutions are expected through some basic theory that the solution will be t-periodic as well. So the solutions will be t-periodic. So when the solution is asymptotically stable, then it will converge to a periodic orbit rather than an equilibrium point, as this case is with autonomous systems. So the central question there is, does a numerical method preserve the periodic dynamics of the original system? We're going to start with this simple case to start with. So why must we study the stability theory? For an autonomous system, we can see that it's very simple. You've got an A, which is a coefficient matrix there. It's linear because the matrix A would be a constant matrix. So then your focus will be just studying the eigenvalue structure of the matrix A. If it's periodic, then we have A depending on T, but it's still linear. Remember that it's still linear. So then we are going to be talking about the flow K because we are talking about a periodic coefficient matrix. It is in the discrete sense. We have this, if we were to discretize this, perhaps using some kind of elementary numerical method, then we would obtain a system of this form in replacing that system. And it is this system that we would like to study and see what happens. The fundamental matrix in the linear periodic case, as we have seen, we've got this. In the fundamental matrix situation, we've got this as the situation. Okay. We define the monodromy matrix to be M to be equal to phi of T. The eigenvalues of M will be given by lambda I, and the stability would then hinge upon rho of M being less than 1 as a standard stability theory. Okay, so let's consider the scalar situation. Looks the same if we were to go back to the to this. This is now not a matrix, it is a scalar. It is a scalar system, and therefore this A of T is just going to be a function A which depends on T. So that's what we are talking about here. We know the solution. Remember, the solution is well known. It's a separable equation. It is easily solvable, and therefore we say that there is only one multiplier in quotes, and that multiplier is exponential of the integral of A of S ds. So that's what it is. That's from an elementary differential equations theory. Now, so the system admits exponential dichotomy on R plus if there exists a K greater than, with a K and alpha greater than 0 and a projection P such that the following is the case. So we say it admits exponential dichotomy if these two conditions are satisfied. Now, the interpretation of what this exponential dichotomy is that we have a stable subspace where the exponential decay, the exponential decays forward in time, and unstable if the exponential decay backward in time. So that's what it is. It's a standard. It's a standard stability theory kind of approach. So this is equivalent to what we normally would call hyperbolicity in the periodic case. So we have a system that is hyperbolic, a system that is hyperbolic, depending on what the eigenvalues look like. The eigenvalues are negative, it's hyperbolic. It's a hyperbolic situation and convergent. If the eigenvalues are positive, it's hyperbolic. It is not convergent. Okay. So we have a theorem which is from a few decades ago, 1978. For a periodic linear system, the system has exponential dichotomy if and only if no Floquet multiplier lies on the unit set. You understand that as as equivalent to hyperbolicity. If there is no eigenvalue that lies on the unit circle in a normal system, non-periodic, linear, then you would conclude that the system is hyperbolic. In the same manner, the non-autonomous system has exponential dichotomy if and only if there is no Floquet multiplier that lies on the unit set. So it's analogous. It's an analogous situation. Okay, so here we are. Let's consider a one-step method that might be used to solve a particular system, non-autonomous system. We discretize it. We use a one-step method. A one-step method, and it's normally given by xn plus 1 is equal to some situation, which would be essentially a matrix, but now it depends on age. That's the key. It depends on age, and we've discretized so that we have created a system using this k is equal to t over h. In other words, those are the number of steps. It's a fixed step size that we're talking about here at the moment. And then this is the dichotomy matrix, where you have taken these multipliers and you multiply them together, and there's k of them, because there's k steps. Okay. Now, then we can obviously do the eigenvalues of this matrix MH, and then our goal is to ensure that these are equivalent to the original eigenvalues of the system. If that happens, we're happy. If that doesn't happen, then we are in trouble. Okay. So the difference equation then looks like this. The dichotomy exists. If this is the case, we are using that theorem that we've alluded to earlier. So the main theorem in the linear case then is the following. Let x prime be a of t of x. Then we assume that the system admits exponential dichotomy. In other words, in codes, we're saying it's hyperbolic. So assume that the method is consistent. The method is AN stable. We defined AN stability to be a linear in linear stability theory. We're not going to discuss it further, but generally AN stable is a property of some systems in which we assume that at the very least it possesses the property of stability. So H is sufficiently small. Sufficiently small then is a very subjective term, but essentially it means that it is so small that we have a situation where there is a stability of the numerical method. Then the discrete system admits exponential dichotomy. So in the linear case, if you make H small enough, then the numerical method, so long as it is consistent, it will, and AN stable, then it's going to inherit the property of exponential dichotomy that comes from the system. So we are happy in the linear case, so long as those conditions are satisfied. I'm not going to have sketched the proof of that result, but we're not going to go into detailed discussions of it. Okay. And then we have a corollary. The corollary is says that if all the eigenvalues of the dichotomy matrix are less than 1, then the eigenvalues of the dichotomic matrix of the discrete system, the numerical system, is also going to be less than 1 for sufficiently small h. It's just a restating of the theorem in the sense of the spectral, in the spectral sense. Okay. So let's look at the linearized explicit midpoint. The linearized explicit midpoint. I'm again We are not going into the details of the derivation of that method, but it is just a matter of taking that system, the original system, the one that has an F, this system, sorry about that, let's go back. This system is the non-autonomous system, this one. And then what we are doing is we are discretizing it using the linearized midpoint, explicit midpoint. Another day we can discuss how to derive those methods. This is essentially a collocation method, a special collocation method with a collocation parameter called C1 is equal to a half. That's what it is. But we are not discussing collocation methods in general, but this is it is a linearized collocation method, midpoint, so the collocation parameter is a half. Okay, now we do a test equation. This is a test equation, which is this is a simple one with a we know, everybody knows the solution of this method, and then what the solution of this system. The A here, A of t, is just a constant -1 in this particular case. So the discrete multiplier, you see from the from the collocation method, is going to be given by this, where C1 in this particular case would be equal to a half, and T obviously is the period. Okay, so remember that what we are doing is we are discretizing in the sense that the H that we are using, I'm not sure where I put the, yes, the H that we're using is actually going to be such that the number of steps is an integral multiple of H. So in other words, the T being the period, we strategically choose the H such that it's T over K, where K is an integer. So that's the way you do it, but we assume that the H is actually sufficient and small as well. So this is the multiplier, the discrete multiplier, which corresponds in codes, because this is just a scalar situation. The lambda d is just is an eigenvalue, but in the discrete sense, we don't call it an eigenvalue, we call it a multiplier, because it's a scalar situation. Okay, so the stability criterion, as we have stated before, is that the multiplier must be in absolute value must be less than 1. So the midpoint method is unconditionally stable, because I think what you can do is we just say C1 is a half here, and C1 is a half, and then you work this out, and you can see that no matter what K is, this lambda is D in absolute value is going to be less than 1. So then we conclude that the midpoint method, the linear midpoint method, collocation method, is unconditionally stable. For the explicit Euler, there is this condition: K is greater than T over 2. It's just a matter of doing the algebra there, which we're not going to give details of. Okay, so then what we are seeing here, just from this fundamental simple test case, we see that already the explicit Euler is not unconditionally stable. In other words, you have to choose the H carefully in order to obtain stability. And you can see from the this is an example that I gave in my previous talk, which we're not going into now, where we took the logistic equation and discretized it using the explicit Euler. We showed that the stability profile of the system changes dramatically if we don't choose the H carefully enough. In other words, it actually bifurcates into chaos even. Okay. So the nonlinear, we now consider the nonlinear periodic system, in which case we take this to be the system and F is nonlinear. In other words, it's not just A of t. But if we linearize it, and I think everybody knows that remember that we are now talking about a system, we're not talking about a scalar equation. So this is a system, and what we do is we are going to expand this using Taylor series, and then we're just going to truncate from the second term onwards, and we remain with this system. Okay? So we're just linearizing about the periodic orbit and get this. Okay. So this system is a linearized version of this one. Okay. So the fundamental nonlinear dichotomy result, equivalent to the linear dichotomy result that we've stated previously, if a linearized system, the A of ty that we've demonstrated there, if it admits exponential dichotomy, the linearized system, and the method preserves dichotomy. In other words, if we are using a method that preserves dichotomy, then the periodic orbit persists numerically. So, in other words, periodic solution results in periodic solution in the numerical result, in the numerical method as well. If the method is if the method preserves dichotomy. Okay. So we have here an open problem which which has not yet been proved. It says characterized, if for a Runge-Kutta method, characterize the Runge-Kutta stability function R of Z such that this is true. This one will preserve Floquet multipliers. That is an unproven result which is open. Okay. The other open problem, these are extensions now. The multiplier then becomes MH, which is this product. The stability problem of this numerical situation, it remains open as well for variable step sizes, where we have the H not being just H fixed step sizes, but we have HJ, which is variable, as most numerical analysts will tell you. Okay, again, another open problem, the semi-linear P.G.D.A.V. This is now a P.G.D.A.V, it's semi-linear, so we need the evolution family, we need the discrete semi-groove approximation of that in order to be able to determine the Floquet theory of a numerical method for this semi-linear P.G.D.A.V. That's also open. So if for example, one were to design a 5-year program, we would discuss the Runge-Kutta numerical Floquet classification, the dichotomy preservation in Banach spaces, In other words, we're moving away from the Euclidean space, and we are now looking in general spaces. The adaptive multiplier tracking is also something that would need to be investigated in this program. A PDE periodic attractors, and then we then look at software implementation and also such results. So the key conclusions, as I conclude, we have introduced the numerical flow K multiplier, which is analogous to the continuous one. We have linked AN stability to dichotomy preservation. We have provided a rigorous linear theorem. We've opened nonlinear and PDE extensions of these results. Now remember that we have not actually looked at there are some results in our 2023 paper which talk about BN stability, which is a nonlinear stability theory of periodic systems. And with that, I would like to conclude. Unfortunately, my references didn't combine properly. So thank you very much, and thank you for the invitation. And I would like to invite questions if there are any.
Thank you, Professor Khumalo, for your nice presentation about the numerical solution of Floquet theorem. So, from audience, please, any questions? Anything? Anyone? Please, this is a chance for you to know the things. Anyone? So, no questions from audience. Just I want to ask you one simple question. So, what may be the possible applications of this numerical Floquet theorems? So, where actually we can use in dynamical systems?
Well, the main application of this is when we are talking about systems with seasonal variations, and periodic systems actually appear almost everywhere. In mathematical biology, we have periodic systems. In physics, string theory, and also various other areas, we have periodic systems which appear there. So periodic systems actually appear almost in every area of science and engineering. Yes. So then, because we've looked at a simple linear situation, but in many cases the systems are non-linear, in fact strongly non-linear, and then you will need, your only source of solution is numerical.
Yes.
And if you cannot trust the numerical methods to replicate the system in a simple one, like we have demonstrated, then how can you trust it in a system whose solution you do not know, where the only source of solution is the numerical one? So that's where the understanding of numerical flow K theory is critical because of that.
Okay, so any suggestion from our new researcher in this area?
Okay, my suggestion is this is highly restrictive. What we've given is highly restrictive. And in fact, in our 23 paper, actually, the only method that we discussed was the collocation. In fact, it was linearized, even linearized collocation methods, which would include the midpoint method, the Euler method, the explicit Euler, the implicit Euler, and we derived the results for that. For even going further and even going to the Runge-Kutta methods generally, that is something that has not been done. So that's an interesting area. And then going even a little bit further and saying, okay, let's do a variable step size situation. That's also another area of research that is also open. And then you can even move to more complex methods where you are looking at how they behave. The method that we used in order to determine the stability of a numerical method is something called stroboscopic sampling. If you remember, in our presentation, we said that the step size must be an integral, the number of steps must be an integral multiple of the step size, so that we sample an integral number of times in a period, so that then a fixed point then becomes a periodic solution. And so that's also something that is what happens if the step size is not an integral multiple. Then how do we determine the periodicity of the solution? That's also an interesting problem. So those are just pointers of some of the problems that might arise from this, which would be a good master's PhD program.
Okay. So thank you once again, Professor Khumalo. So this completes your presentation. So you will be there because we have another lecture right now, Professor Sharma. So thank you once again.
Thank you so much.
Court answer.